being very interested in the past couple of years. And it kind of started more on the abstract side with this paper in collaboration with Haya Norton and Giulio Ruzza, but then it morphed to some more applied settings. Like in particular, I will talk probably about these parts, and will explain how these Koshi kernels are important, and they're important that they are explicit for applications, right? Numerical application in particular. Okay, so first of all, let me, in this audience, probably there are many people that are familiar with the standard Riemann-Hilbert problem, but mostly in the integrable system community, the Riemann-Hilbert problem is considered as a matrix valued problem on the plane, or maybe on the Riemann sphere, right? And the prototypical Riemann-Hilbert problem is something that goes as follows. You want to find a matrix, let's say of size n by n, which is analytic together with its inverse and bounded on the whole plane, and for example satisfies a boundary value problem on a circle or some other smooth curve, right? So the plus side as usual is the left side, the minus side is the right side, and on this contour there is defined a matrix which we can call the jump matrix. Now, as everybody who has tried to solve a Riemann-Hilbert problem should know, is that there is an obstruction, Your Honor. The first obstruction that can happen is if the index of the determinants of the jump matrix is not equal to 1. Okay, so in that case, sorry, it's not equal to 0. What is the index is just the increment of the argument of the phase of the determinant of G. If that is non-zero, then there is no chance that you can find an analytic matrix valued function with these properties. But even if the index is 0, there are other issues that can occur that can prevent the solvability of this Riemann-Hilbert problem. And now it's a little, well, it goes into the issue of the partial indices of a suitable triplets operator. This problem is the exact equivalent as the Birkhoff theorem on classifications of vector bundles on the Riemann sphere. Okay. And so in other terms, to say that this Riemann-Hilbert problem is solvable is the same as saying that the vector bundle with this transition function is trivial vector bundle. So somehow in integrable systems, we are interested in the trivial vector bundles rather than non-trivial vector bundles. In an integrable system, the typical application involves that dependence on the jump matrix, a particular type of dependence on additional parameters, right? So that these existence, non-existent issue is a hit and miss condition. Now, we want to do something similar on a Riemann surface of genus G. Okay, so the picture that we have in mind is now, let me draw some Riemann surface of genus 2, and then you can imagine to embed my disk on the Riemann surface, choose a matrix valued function on the contour, and ask for a similar solution of a problem. So can we repeat this problem? The answer is no. Just a second there, because I need to flip, but okay. The answer is no, we cannot. Because if we insist on the jump matrix to have index 0, the determinant of the jump matrix to have index 0, then you are kind of forced to allow pose in the solution of your Riemann-Hilbert problem. You can even try, and it's a good exercise, try for the scalar problem. Okay, the standard approach, you take a logarithm, then you start doing some gymnastics with Sochowski-Plemeli. You face the first hurdle is that what you use for the Koshi kernel, then you have to choose appropriate Koshi kernel, etc., etc. So even the scalar multiplicative Riemann-Hilbert problem is not trivial at all, and then immediately you are faced with this index issue. Now, if you insist on the holomorphicity of Y, and you can't insist on the holomorphicity on the inverse, but you can insist on the holomorphicity, or vice versa, of course. You insist on the holomorphicity of Y, then it turns out that generically, the best you can do generically is to allow the index of your degree, determinant, not degree, of the determinant of G to be NG. N is the size of the matrix, G is the genus. And of course, this matches with the experience that we have in genus 0, where the standard problem has index 0. Here, the standard problem has index n times G. Now, algebraic geometers know this very well, why you make a little bit of, why ng is the magic number here. Because you're studying, if you're studying a vector bundle on, let's call it this vector bundle E of degree ng of rank n on a Riemann surface, then you can use the Riemann-Roch theorem, which tells you that H0, which means the dimension of the holomorphic the dimension of the space of holomorphic solutions. So what are holomorphic solutions? They are the rows of this matrix, right? Each row is a solution of this Riemann-Hilbert problem, and if you have n of them linearly independent, then holomorphic, then you have your matrix Y. There is initial normalization, but okay. And Riemann-Roch tells you this magic number, right? That turns out to be H1 plus n. Now, this H1, for people in algebraic geometry know exactly what I'm talking about. Maybe people in integrable system audience may not know. So this is another dimension, but all the things that you need to know right now is that generically this is 0, okay? And so generically this is 0, and so generically you will have precisely n linearly independent row solutions of your Riemann-Hilbert problem, out of which you cook up your solution of the Riemann-Hilbert problem. Okay, and then I will define directly the non-abelian theta divisor as the collection. Well, why we call it divisor, we call it laser, right? But it's the collection of all these vector bundles for which this H1 is non-zero, 1 or higher. Okay, all right, so now I want to convince you the inevitability of this construction, which is due to Turin, which is first very well known to Eger here, and probably a few others, but not as widely known as I would expect, for example, in algebraic geometry. I asked around, and essentially, and nobody out except for Eger knew of this. Maybe Dima Korotkin knows, right? But knew about this parametrization of the modular space of vector bundles, which is a pity because it is extremely practical, right? And you'll see what I mean by practical. I mean that you can write formulas, not the usual, exact sequence that has more or less meaning depending on whom you're talking to. Okay, so since our index, we decided that we go after problems of index ng. It means what? It means that if you take the determinant of your matrix solution of Riemann-Hilbert, it's a piecewise defined function outside of the contour, which has, outside of the discontinuity, which has ng zeros, a total degree, let's call this divisor, Turing divisor, okay? Let's simplify things and imagine that those are simple zeros. So there are n times g, simple zero of your determinants floating around. Now, if these are simple zeros, then it's easy to prove that the matrix evaluated at this point has co-rank 1, which means that you can find a row vector solution, right? In the spanning the kernel, and that we call them, let's call it Hj. Of course, it's defined only up to multiplicative action, right? So you can multiply by any non-zero number. So if you want to have higher multiplicity of zeros, then it's not as straightforward. You find in this paper with Haya and Giulio the definition. But for the sake of this talk, let's keep things as simple as possible. Okay, so the Turing data is precisely the collection of these data, the divisor, right, the points where the determinant vanishes, and these vectors in projective space. They are called Turing data, and the statement is that they are moduli of the space of vector bundles of degree G up to some obvious action. Okay, so in other words, they are parameters to parameterize vector bundles. Why they are convenient rather than other versus other moduli that you could find? Well, we'll see in a second. Now, with an eye to the applications, let me introduce the Koshi kernel. So in integrable system community, right, there are a lot of people that are interested in asymptotics, right, of MLS, orthogonal polynomial, KDV, small dispersion, long time, whatever, high degree. And the magic tool for the last 20 years has been the steepest descent Dive-Joule method. So what is the key of the Dive-Joule method at some point is the analysis of the error term. So that to analyze an error term is the same as analyzing infinitesimal deformations of, to write a Dyson kind series for the infinitesimal deformations of some particular Riemann-Hilbert problem. Or if you wish, in this context, infinitesimal deformations of vector bundles. So imagine that you take your jump matrix G, the index NG, you add a small perturbation, epsilon times delta G, and you want to find the infinitesimal deformation at the epsilon equals 0, which let me denote simply by y dot. In other words, I take the derivative with respect of epsilon of that, right, and set epsilon to 0, and you get this non-homogeneous Riemann-Hilbert problem. So the game is then the following. Suppose I have my solution of the Riemann-Hilbert problem. Can I write the solution of this non-homogeneous problem? Well, what do we do in genus 0? In genus 0, you have the Koshi kernel, which is a scalar object, okay? And then you can write this formula. You can check using Sokowski-Plemelli that this provides precisely the solution of this non-homogeneous Riemann-Hilbert problem. Why this is important? Again, precise because for people that are familiar with the steepest descent Dive-Joule method, this is essentially the error term at some points of the analysis after you open the lenses, etc., etc. So you have to guarantee that you can solve the error term. And in between, well, then you have a little bit of analysis. You look at the norm of the perturbation, and then you can guarantee that the solution exists or not. And it's relatively simple. Now, the problem is this. What happens in higher genus? What should I put instead of that? So this is a scalar, right? Okay, it's promoted to a matrix by just sticking an identity, but it clearly makes no sense in a higher genus. It should be something which depends on two variables, z and w, or let's say 2 points, and it's a differential with respect to one and a function with respect to the other. Now, this object has a differential with respect to w as a simple pole when w is equal to z, and a simple pole at infinity, right? Oh, sorry, yeah. So it has a simple pole at infinity. And as a function, as a meromorphic function, has a simple pole when z is equal to w, and a simple zero when z is at infinity. Now, on the Riemann surface of higher genus, infinity means nothing. It's just a point, you choose a point. So I'm just alerting you to the necessity, which you do not think about in genus 0, that you must choose some kind of reference point, infinity. What is this infinity for people in the Riemann-Hilbert community? Well, it's the point where you say my Riemann-Hilbert problem is normalized, right, for example. Okay, your solution has to be identity infinity. Okay, so that's where these Turing points come in handy. Now, remember these Turing vectors that define, they're row vectors, right? So you have to think of them as rows. And first of all, I want to convince you that they are convenient as to just get a hold of this non-abelian theta divisor. This is the non-abelian theta divisor. So how do you do that? Well, you cook up the following matrix of size ng, so it's a tall rectangle, right? You stack them one on top of the other. Then you choose any basis, for example, the normalized basis of holomorphic differentials. And with this notation, I simply mean the square matrix diagonal, where you evaluate this particular differential at each of the single Turing points. And then you cook up this matrix, right? So this is a tall triangle because it's this rectangular times this one, right? And you stick G of them, and now you get a square matrix of size ng times ng. We call this the Brill-Noether-Turing matrix. And the little theorem, which is not that difficult to prove, in fact, we just basically need to understand what those symbols are, is that this H1 is precisely the corank of this matrix. And so immediately you'll have a very explicit representation of the non-abelian theta divisor as the locus where the determinant of this matrix is 0. Now, since the determinant of this matrix is defined up to some action of GLN, this is not a function, but it's a section of an appropriate line bundle. But that's the simplest way in which you define a divisor, right? Divisor is the zero locus of some locally analytic function, and that's it. It's the determinant of this matrix. Okay, so it's nice, but maybe it's still not very practical. Let's get further. Now, this Koshi kernel, the Koshi kernel that is used exactly in the solution of the small norm theorem and Riemann-Hilbert problem is this. So it's a matrix, first of all. It's non-abelian, so it's scalar. It's non-scalar. It's a differential with respect of, let's say, W. This is a point on the Riemann surface. It's a meromorphic function with respect to the other variable. And so the dW here, just to remember, right, in some local coordinate. So when W and Z are close to each other, they have a simple pole with residue identity. I gave a name to the next term in the expansion along the diagonal because it's important for application. And then with respect to W is a differential, with respect to Z is a meromorphic function. And it has these divisor properties, right? So this means that with respect of W is a pole at Z and a pole at infinity, simple. With respect of Z, it has a pole at W is 0 at infinity, so 0 of the whole matrix, right? And then it poles along these Turing points. And now there are additional conditions. There are kind of linear constraints, which are given as follows. So these, when you set W near one of these Turing points, you take the corresponding Turing vector, you multiply the matrix. So the result should be, this is incorrect, should be analytic as W tends to Pj. And with respect of Z, if I think of it as a function of Z, and Pj is, it's the local coordinate, then the singular part, if you look at the rows of the singular part, they are all in the span of this Turing vector. Now, the key is that these objects, this matrix object, exist and is unique as long as, if and only if, your vector bundle is not on the theta divisor. And then I give a name as a affine connection to this F, because I will mention it later, but I will not spend too much time on this issue. Now, to convince you that this is practical, here is the formula for the Koshi kernel, okay? So these are the matrix entries. These are the holomorphic abelian differentials. This is just the data that we had before, and there's nothing. This is the third kind normalized abelian differential, and this formula defines the unique object, right, that has the previous. Notice that in the denominator we have precisely the determinant of the Brill-Noether theorem, which of course reinforces my statement as before that this exists only outside of the theta divisor. Okay, any questions? Just interrupt if there are questions or comments. Okay, so now we go to the applications, right? So there is one which is more like, let's say, high flying, and Igor knows very well what I'm talking about, and the other one which is very ground based, right? So it's a really application where I will draw a graph of numerical approximation of things that would not be possible without the notion of Koshi, matrix Koshi kernel. Okay, so this, it's only one slide, right? Don't know how many people are familiar with this kind of language in this audience, but so here is a little diagram where, let's see, this is V is the moduli space of stable vector bundles of degree ng. This is the cotangent of said object. This is the connection, so those are connections. So affine connection on this vector bundle with some fixed divisor D is something you can choose as parametrization. Here, so what are, for other, maybe another language that is less mysterious, an affine connection is just an ODE on the Riemann surface, okay? An ODE for a matrix system of ODE of first order with particular structure of the poles. And this M is the monodromy map. So it's like Painlevé, right? So you have an ODE, you have a monodromy map that gives you a representation, matrix representation of a fundamental group, a modulo action of groups, but this is the so-called character variety. It's just representation of the fundamental group. And if I have a reference affine connection, which is constructed precisely using that matrix F on this previous slides here, this F here, okay, which is as explicit in principle, of course, as explicit is this Koshi kernel. If I have that, then I can identify the space of connection with the cotangent bundle of the moduli space. Now, both the cotangent bundle here and this character variety are Poisson manifold. In fact, they are symplectic manifold. This one in a tautological way using the Liouville form, as any cotangent bundle is. This one less trivially, because this is due to Will-Goldman, right? Goldman symplectic structure. Okay. And so the statement is that if you take the Goldman symplectic structure and pull back by using this particular identification, right, of the affine connection and the cotangent bundle, you pull back through these maps to this cotangent bundle, you get the same object, the same symplectic form. Now, symplectic form, remember, is a two form. Okay, so vice versa, because this map is also invertible locally, right, outside of the theta divisor. You can also pull back by the inverse the Liouville form from here. Yeah, you are pulling back in here. And then this gives you a symplectic potential for the Goldman symplectic form. In other words, it's a one form, which has the property that if you take its derivative, you get the symplectic form of Goldman. The symplectic form of Goldman is explicitly writable. I just don't write it in this talk, right? In terms of the matrices of the representation. And so the...
Excuse me, please. Excuse me, I'm just a little bit surprised by this statement that you may, the surface is compact for you, closed or not necessary?
Compact.
Excuse me,
no
maybe
right.
it's not no punctures. You claim that the cotangent bundle has the same symplectic structure as the Goldman one, which is a little bit strange because the cotangent bundle has a zero section, so it's a Lagrangian section. However, the space of local system has non-trivial. Any section is non-trivial, so they cannot be isomorphic.
So you are pointing out some global issue.
Yeah, right.
Right. Okay. It's global.
Okay, locally, of course, if you have non-compact surface, then you can establish an isomorphism. But if the surface is compact, locally, it cannot be possible.
About local, global or local in the moduli space, not in the surface. We are talking. This is a statement on the moduli space, not on the surface, right? Yeah. So whether the surface is smooth, compact, or right.
Yeah. So
well, I mean, I think that. By the way, let me point out here that Igor, yours truly, there is actually the first to have stumbled upon this this identification in around 2001, 2002. Although maybe it wasn't immediately obvious that what he obtained was the Goldman symplectic structure. In the paper, at least, it was. I'm not sure if it was immediately obvious, but essentially it is in there. But well, what I'm saying here is that, let me see if I take this this object here, which is the, so yeah, maybe, I mean, the statement is, maybe this is where it may simplify life here, is that this phi that is defined by this push forward by the inverse monodromy map is not holomorphic everywhere, is meromorphic object, okay? And the statement is that this meromorphic object has a pole along exactly the image by the monodromy map of the non-abelian theta divisor. Not only that, but it has an explicitly computable residue at each point of this divisor, which is exactly minus h1. So in other words, if I take this object and I add the differential of the logarithm of that locally, right, which is locally defined, smooth, this is something with a pole, by definition, essentially, is a pole with residue plus h1 on the non-abelian theta divisor. So the sum is locally analytic, locally, right, near the non-abelian theta divisor. So so the fact is this one form is meromorphic. So I think that should maybe answer part of your question.
Volodya, maybe the simplest answer on your question, you should throw away the zero section of cotangent bundle.
Yeah, but if you take any other section that is gives the homologically the same class, and so you have
locally you can do that outside of this theta divisor.
Yeah, maybe if it's just really outside the theta divisor, of course, this can be. Yes, certainly you can. Okay.
All right. So okay, but I don't want to stir controversy here, right? Maybe they can discuss later. So informally, and here I'd say informally because Poincaré duality on this moduli space is not, I'm not sure how, I'm not that strong in algebraic geometry, right? So because this modular space is a nasty object, and usually Poincaré duality is for compact smooth manifold. So take it with a little bit of quotes, and that's exactly why I put the quotes. But what we are saying is that the Goldman symplectic form as a two form in cohomology is the Poincaré dual to the theta divisor, because precisely you can write a global meromorphic one form whose differential is that. Okay, and this phi is a global meromorphic, and precisely the fact that the residue is that is what characterizes essentially Poincaré, one way of characterizing Poincaré duality. Okay, so now I close this abstract part, right? And now I go to the concrete part. Okay, so more practical, and now I'm going to descend on Earth and stay with the feet firmly planted on the ground. So I'm going to talk about now of the good old orthogonal polynomials on the plane. Okay, so remember that one way in which you introduce orthogonal polynomials in the plane, for example, let's say, just to fix the ideas, let's say that this is the real axis, that you have a weight function which admits all moments, and you construct these sorry about that, stilches. Sometimes it's called Markov stilches function. It's the generating functions of the moments of the measure. Now, then what you do, you try to approximate near the point at infinity using rational approximants. Those are called Pade approximation. So for people that do not know what Pade is the rich cousin of Taylor, right? The Taylor approximation is with polynomials, and Pade allows you to use not just polynomials, but ratios of any polynomials. You choose the degree that you want for the numerator and the denominator, and then you have a Pade approximation scheme. And it's used, for example, in high energy physics to find resonance in other words, masses of particles out of data taken at infinity. All right, so the Pade approximation consists, in this case, in this setting, in finding a polynomial of degree n in the denominator and a polynomial of degree n-1 in the numerator, such that the difference between this Markov function and this is of the highest order that you can make it as z goes to infinity. If you count the number of parameters here and the number of parameters there, you realize that generically you can make it as small as this order of tangency between the two expressions. Now, of course, this is, if this content goes to infinity, it's in the sense of asymptotic expansions. Okay, so the denominators are famously the orthogonal polynomials for the measure. And so now my goal is to merge orthogonal polynomials, Pade approximants, etc., with Riemann surfaces. And there is not much in the attempted yet in this, except for the 3 papers that I mentioned before. There was a paper by Fazlini Zhu, where they study kinds of ad hoc orthogonal quote-unquote polynomials on elliptic curves. And in fact, I will focus on this example, on a similar example later on. And then there is a paper of Christophe Charlier, where they, starting from some recent development in the study of the statistics of the Aztec diamond, and I think that Alexei Borodin will talk about something very closely related to that later on in this conference. Arno Keulers, Maurice Deutz, and Christophe Charlier, and then Charlier took the ball and ran a little bit with this. They found out that the model can be solved in terms of certain matrix orthogonal polynomials on the plane. And Charlier realized, and also implicitly, they before Euler's and Deutsch realized also that these scale matrix orthogonal polynomials in the plane can be interpreted as actually scalar orthogonal quote unquote objects, polynomials, let's say, or really they're sections of certain line bundles on a Riemann surface, which is not quite, but just for the sake of the discussion, is the spectral curve of the weight matrix. Okay, so there are two ways in which you can generalize orthogonal polynomials when we go on a Riemann surface. I'll flash this one, but I will discuss the other. So this one consists in the following, starting from this following, gymnastic. Take this dx and split it into square root of the x and square root of the x, and say that these are half differentials. Okay, and then the orthogonality is just an orthogonality between half differentials, or if you want to say things in a fancier way, sections of the semi-canonical line bundle with a fixed pole divisor, right? Because they have poles only at infinity. The other way is to use things that are less fancy, just meromorphic function with given pole divisor of degree G somewhere, and poles of increasing order at a given point. So I'm going to be describing that because it's where actually so far the only case in which I've done some asymptotic analysis, and I can show you picture and numerics. Okay. So what is this Pade problem on this Riemann surface? So we have a Riemann surface of genus G, and a generic divisor of degree G. So here we have genus 2, divisors 2 points. A fixed point, which we call infinity. Well, I will also choose a local coordinate near infinity. So this is essentially starting resembling very much the data of the famous Ricciardo constructions for K-Pita function, and indeed there is a connection there. And then you, in addition, however, you have a curve, basically your contour of orthogonality, gamma, and a measure, a density, a measure really, or d mu on gamma, completely arbitrary, well, I mean, within reason, right? Smoothness reasons. Okay, now here we need the scalar Koshi kernel, which is just the same as the matrix Koshi kernel minus the matrix, right? It's just one, it's a scalar. So here are the properties, is well known. Now, except that in genus G on a Riemann surface, people that study Riemann surface know this very well. There is not a unique Koshi kernel. There are families of Koshi kernel, and they are parameterized by G parameters. Okay, G is the genus, complex parameters, and they take they appear, these complex parameters. Well, they can appear in many ways as you prefer, more or less. But the simplest way is to think of them as a divisor. In other words, these G points, right? So the choice of G points on the Riemann surface. So here is, you've probably glanced already at this example, right? This is genus 1 in terms of Weierstrass zeta. And A here is the point of the divisor. So we are in genus 1. So I'm thinking of the elliptic curve in this way, right? As the quotient of the plane by the lattice generated by Z and tau. Z, where tau is in the upper half plane. Okay, so this convinces you that at least you can make it concrete in some example. You can make it more than this example. Okay, so now what we do, we take the measure and the contour and integrate the Cauchy kernel with respect to the function. This Q is the variable with functional dependence. So this P is a differential. So the result is actually not a function, but it's a differential. It's a differential with a discontinuity on gamma. Okay, and then by Sokotsky-Plemeli, you can say that W of P plus minus W of P minus is 2 pi I times d mu, where P is the point in gamma. So instead of, now there are no polynomials on Riemann surfaces, right? What replaces them? Well, you take sections of line bundles. Okay, so maybe this terminology is not very familiar, but it simply means L. This L stands for the space, the linear space of meromorphic functions with a pole at this point infinity of a degree of order n at most, and with at most simple poles, or whatever the multiplicity is, at this divisor D. So they, in genus 0, there is no divisor, right? And so that's exactly the space of polynomials. In higher genus, it's a space of meromorphic functions. Okay, so you fit, let's call Pn an element in this space, and the Pade problem is the problem of finding a Pn of fixed pole degree at most, and the meromorphic, so meromorphic differentials, so that's why it's in a strange font. So K here is a canonical, which simply means it is a differential with a pole at most of order n+1 at infinity, such that when you take the ratio, so this object is a differential, this object is locally differential, and you look at the divisor of these things, so in other words, the zeros and poles, etc., there are outside of the point of discontinuity of W, so it has zeros of twice the order D there, and a zero of this order at infinity. So this is a algebra geometric formulation of the standard condition of Pade approximations in genus 0, right? There is no such term. You can divide by dz, and you get the standard good old Pade approximation problem. Now, first theorem, which is not as trivial to prove as in this genus 0 case, is that these denominators are functions, right? And they are orthogonal in this sense. This is non-Hermitian orthogonality, right? Sometimes called, because there's no complex conjugation. Okay. So the first thing that should be familiar for people in integrable systems. Okay, so then what does survive?
Sorry, Mark, and who are the coefficients on the right-hand side? Because usually for polynomials, these coefficients arise if you normalize them specially, like the eldest coefficient is 1. Otherwise, yes, you can make them just unities. And who here you don't have any normalization. So who are these coefficients?
Yes. Okay, so good point. Let's see here. Okay, so you start, how do you start, right? So that's where this local coordinate near infinity comes into play. So Z is this local coordinate infinity where Z of infinity is infinity, right? So it maps the disk around the point at infinity to the outside of the unit disk in the plane. And then you define these objects, zeta j of Q, which are given by this residue formula in terms of the Koshi kernel. Sorry, here it's the same Koshi scalar kernel that we had before, right? Depends on the point of infinity, depends on the choice of divisor B, but I didn't want to overload the notation here. So these replace the monomials. In fact, in genus 0, these are literally the monomials, right? In higher genus, there are some convenient choice with implicit normalization of monomials. So let me call them monomials. And then the normalization that you were asking for is exactly to impose that the leading pole as coefficient 1 of the highest zetas. Okay, so then what do? You take, like you do for orthogonal polynomials, right? Nothing particular. It's more like bi-orthogonality here. You take the bi-moments, so you stick this zeta j, zeta k, you integrate, you get this matrix, which is obviously symmetric. And then a little exercise gives you, in terms of this formula, which, okay, where you appear, the Koshi kernel appear. Then define this determinant, which is the analog of the Hankel determinant of the moments of orthogonal polynomials, except that it's not Hankel because they don't depend on the sum. And then many things happen. Like, for example, you have the Heine formula for these orthogonal quote-unquote polynomials. sections of this line bundle. So it's this multiple integral, like people in orthogonal polynomials know exactly what the Heine formula is. And there is a 2x2 Riemann-Hilbert problem, which is exactly the crucial thing where you can, you start putting the finger that now I need the Koshi kernel, I need, because I want asymptotics, right, for large n. And then you have to understand how this Riemann-Hilbert problem in higher genus works. Now, what doesn't survive is the return constellation, but you can replace it by a 2G plus 3 recurrence relation. Now, of course, multiply by a function which has a single, not simple, but single pole at infinity. And then you know by the Weierstrass-Dapp theorem that the smallest pole that you can have is G plus 1. Okay? It's G plus 1, and that's why when you multiply by this, then you can construct 2G plus 3 recurrence relation. But I'm not going to focus on that. Okay, so what is this Riemann-Hilbert problem? So that is the equivalent of the focus. It's Kitaev problem for orthogonal polynomials, right? Which is the basis for the application of the steepest descent Diffie method. Now, the difference is this, that it's a 2x2 matrix still, analytic and bounded outside of the contour of integration. Analytic outside of the contour of integration with this jump condition. Now, note that the first column of this matrix consists of functions, and the second column consists of differentials with discontinuity along gamma, but they are differentials. Okay. So in the first column, these are the pole divisor property. So it means, what does it mean? It means that the first column has poles at this divisor D and the poles of this order at the point at infinity. The second column must be made of differentials. This K indicates just sections, local sections of the canonical divisor. They must have zeros at the divisor D and zeros at infinity of the indicated orders here. This is the order of 0. And then at infinity, this is the normalization where you use the local coordinate, right? And that's this z to the n sigma 3 is familiar to everybody in orthogonal polynomial business. What is strange is a little bit the appearance of this dz, well, inevitably, because the second column must be a differential, right? So note, it's not harmless, the thing, because this means that the first column has a pole of order n, and the second column has a 0 of order n minus 2, not n, right? Because dz has a pole of order 2 at infinity, and z to the n has a 0 of order n, so it's n minus 2. So the way you count the order of poles changes as an effect of the fact that those are sections in the canonical divisor. How am I doing? Okay, 10 minutes. That should be okay. Okay, so what about existence? So I don't think I will manage to do all of that, right? But what about existence? Well, you look at the determinant, you discover immediately, as usual, that the determinant is actually an honest differential without jumps, because the determinant of this matrix is 1, but it has a double pole at infinity. And so, by degree counting, it must have 2G zeros. Aha, 2G. 2G is precisely our favorite degree, right? Mg, n is the size, and G is the genus. So that these are the zeros are the Turing points. Now the question is, but how do you prove, for example, uniqueness or existence of this Riemann-Hilbert problem? The standard argument used in orthogonal polynomials does not work precisely because the determinant has 0. It's not the constant 1. Right? And so it's a different story. And the theorem is, well, first of all, one could phrase it as follows. If these Turing data defined by this object are generic, then essentially you can prove uniqueness, right? But now I'm trying to talk to people that do not know or are not familiar with this notion of Turing data. And so I'll give a description which is entirely self-contained and does not rely on anything else but the moments. And here is what it works. The solution of the Riemann problem exists as unique if and only if that determinant, remember this, the n is the determinant of the matrix of the moment of by moments. Okay, if and only if is non-zero. Now it's not the same theorem as in genus zero. In genus zero, if the solution of the Riemann problem exists, it is unique, right? Because there is a Fredholm alternative, being that the problem is of index zero. Okay, if it exists, solution, it is unique. But here, and if it is not unique, it does not exist, right? So, well, one way in proving that the Riemann problem does not exist is to prove that there are too many solutions in genus zero. Here is a little bit different, precisely because the index is not zero. And how is different? It means that if this determinant is non-zero, then the solution exists and it is unique. But if the determinant is zero, the solution may exist but not be unique, or it may not exist. Okay, and that because when you could be in a case where either the pairing of the orthogonality is degenerate and then essentially doesn't exist, or you happen to fall on the theta divisor, and then you have too many solutions, okay, on the non-abelian theta divisor. And then you have existence, but not uniqueness. So in that, anyway, so these formulas kind of mimicking the same formulas that happen in genus zero. Okay, so example, right, where I can give you some concrete. So genus one, Harnack curve, a real curve with the real ovals. So it's something that looks like this, right? And then you take a measure on, well, let me just draw the picture here. I take a measure on one of the real ovals, real positive measure now. So this real oval here corresponds to this line here. The measure doesn't have to be any particular property except that it has to be full support. And I am assuming that it's analytic in a small strip around the contour. And then you set up your orthogonality, right? You have to construct your monic polynomials, and here is easy, right? Here is the first is 1, then there is Weierstrass zeta plus a pole at your divisor d. Then you can use Weierstrass p, p prime, etc. So those are, and so on and so forth. Those are your monic polynomials. Then you start Gram-Schmidt, right? Being that the pairing is positive definite, everything is real, it works exactly like orthogonal polynomials. The existence is guaranteed because the matrix of moments you can prove by standard Andreev manipulation. It's a positive matrix, so no problem. The n is positive. The orthogonal polynomial exists for any degree. Okay. Then you study structure of this polynomial. Let's call them. Sorry, I call them polynomials, but they're not, right? So they're linear combination of these things. You study structure. Ask, for example, standard structural properties of orthogonal polynomials. Where are the zeros? Do they interlace, etc. So they have n+1 zeros, and they are all on the support except possibly one, which can be in the other oval. This d is the divisor. And then you ask asymptotic, right? Let's send n to infinity. What can we say about the asymptotic of this object? Can we write formulas? Well, the answer is yes, right? And since I'm running out of time, so this is the Riemann-Hilbert problem that you have to start with. Now you can work with elliptic. Basically, now you divide by dv, and you can just work with elliptic functions, right? It's a 2x2 matrix of elliptic functions with particular jump condition and particular poles, right? Note this n and n-2 precisely because of the index issue. Okay, and then these are the divisor at this extra divisor, here genus is 1, so there are only 2 zeros for the determinant. And so here you have a first instance in which when you do your steepest descent analysis, you need to construct the G function, open the lenses, all this more or less standard machinery. At some point you are faced with the error analysis of the error term. And to construct the outer parametrics, etc., then to prove that the error term exists, you need the Koshi kernel, the non-abelian Koshi kernel, and that's where you need the Turing divisor and Turing points. This is the Turing divisor, these 2 zeros. It's kind of baby version, right? But where you already touch the necessity of the construction of the Koshi, non-abelian Koshi kernel. Okay, so because my time is running out, let me just show you the output of this asymptotic analysis, just to show that it's concrete, right? So these are numerically computed. The black is the orthogonal, the result of the orthogonality. The horizontal axis is just from 0 to 1 is this cycle, right? The oval, and this is the value of the real function. The black is obtained by Gram-Schmidt with Mathematica, and the red is the result of the approximation. Here the convergence is super exponential. One can prove that because of the property of the measure. These are the formulas if you want to look at them, but they are the explicit formula in terms of what else can it be? Jacobi theta function, right? There's nothing else it can be. But those are asymptotic formulas, and this is the order of the approximation that comes out. And then, well, the density of zeros also one can compute, and so on and so forth. I have 1 minute, and then maybe. No, that matrix of bi-orthogonal polynomials I will not discuss. And I will just to mention a separate problem that one tackle along this line of thought. And this is a construction of a generalization of Eger's algebra geometric tau functions. In that case, you have more or less the same data, the measure, in addition to the standard algebra geometric construction. You have the measure and the contour in addition. And then you start basically doing orthogonalization with respect to sequences of line bundles, one that depends on T's and S. So maybe just to say something meaningful, let's say that you use instead of the so let's put it this way. You use as you take the Baker-Kaiser function of the algebra geometric, right? And then start differentiating with respect to T1 the first time. And you call these objects psi n, and then you can use those as your monomials. Then you do bi-orthogonalization with respect to the measure. Okay, so that provides you a pairing between these 2 spaces, and in this case, you can show that the pairing is degenerate if and only if a certain tau function vanishes, and that's the formula. So, what just to end? So, what the ingredients? So, this piece is the standard algebra geometric tau function in 2 sets of independent variables, infinite variables. This is just a linear expression, and then there is these determinants of bi-moments, which can also be written as an n-fold integral, which is reminiscence of, for example, matrix or matrix models, right? Okay, so and these objects satisfies both.
Marco, sorry, you should find a time to stop your talk because we are already 2 minutes late.
I'm on page 31 of 32. So I'm just saying that this solves KP in both variables and also version of 2 Toda, and then I can stop here. Well, I'll just leave it there for thank for your attention, and if you have any questions. Yeah.
Okay, thank you for your talk. Any questions, comments? I have a general comment. probably I would like to mention that a lot of credit should be given to people who did Riemann-Hilbert problems on Riemann surfaces in 60s and 70s. Actually, the notion of matrix Koshi kernel of different type was introduced in works of Zverovich, Muskhelishvili, Rudin. They were not working with non-trivial vector bundles. They mostly worked with trivial ones, but and that's why their Koshi kernels was meromorphic or multiplicative. There was a bunch of such kernels. So I think it would be fair to say that this story started more than 50 years ago.
Yes, but I tried to trace back those references to Rodin, Zverovich, and actually the notion of Koshi kernel goes before Zverovich is Benke. We have found Benke is 1930s or 40s. Now I forgot a little bit. So it's a German, and Benke and somebody else. So they had this.
It's actually very natural. As soon as you are dealing with Riemann or jump problems, you inevitably dealing with Koshi type integrals, and you introduce Koshi kernel. So I just want to mention that the whole definition or starts much earlier. Simply you forget to mention that.
Thanks for the reminder. Yes, of course, but this is wasn't the focus. The talk is many people have contributed to this notion, right? Mostly in a scalar case, I couldn't find the matrix in the literature, but I'm sure that you can point out.
I can give you literature. Rudin's book is
it doesn't have the matrix. Read it back to front. They don't have matrix kernels there. No explicit formulas at all, and not even there's not used matrix kernel. But maybe I'm mistaken, of course. Right? Yeah. Anyway, so thanks for the
And actually, one more remark, if you go back to the tau function of 2D Toda, actually the explicit expression for tau function in terms of theta function was in my old paper, as far as I remember.
You mean this one, right? So with the quadratic expression times the theta function?
No, theta function, and it was this formula included n as one of the time variables.
Okay. I missed that probably.
Okay. More questions, remarks?
If you can.
If no, then thanks, Marco, for your interesting talk. And we meet